Welcome to the online lectures for software engineering. In today's class, we'll be studying with the system engineering, the second chapter of Unit 2. In the Unit 1, we have studied the different set of principles. The first topic is computer-based systems. Now, what is a computer-based system? Now, the computer-based system is defined as a set of arrangement of elements, and these elements are combined so that a specific task can be performed, so that you can achieve a predefined goal. And this predefined goal is achieved by processing information. Now, what happens in processing information? When you give input, based upon that input is going to be processed, and based on that, you're going to get an output. So that is how computer-based systems are going to behave. Now, the goal is to support business functions. Now, in here, as you're focusing on software engineering, so in software engineering, we are going to focus upon the development of different softwares. Now, in here, these softwares are, the responsibility of building this is under a specific organization or a specific business. So the goal of computer-based system is to support the business function or to develop a product that can be sold to generate business or revenue. That is when you have developed a particular software. Now this software, it can be used for generating business. That is when you sell this particular software, you will be able to get profits. You are going to get profit out of it. The goal is the computer-based system makes use of a variety of system elements. It is going to make use of different elements within the computer-based system. Now coming on to the different components of the computer-based system, the computer-based system has got 6 different concepts. The first one is software. Now we very well know what is a software. A software is a computer program, or you can say a set of instructions. And it is also data structures and related documentation that serve to affect the logical method procedures of control that is required. Now based upon a particular software, based upon the input that you're giving, it is going to process and give you the specific output that you have designed. The next is hardware. Now in here, this is software, it is internal behavior of a particular program, whereas hardware, it is an electronic device that provides you with computing capabilities and interconnectivity devices. Now what are these interconnectivity devices? These interconnectivity devices, now as connectivity means how you're going to connect to a particular, how you're going to connect, you'll be able to connect and communicate whenever you're connected to a network. That is, interconnectivity devices is a network switch or a telecommunication device. So these are your interconnectivity devices. Now these interconnectivity devices enable the flow of data and electromechanical devices. Now what are these electromechanical devices? These electromechanical devices, it can be sensors, motors, or pumps. So this hardware, it is a combination of interconnectivity devices and electromechanical devices. Now in here, by making use of these two things, it is going to provide you with an external world function. That is, in here, if suppose you've got a sensor, suppose you've got this fire alarm sensor. Now this fire alarm sensor, what is the job of fire alarm sensor? It is going to sense if a fire is detected, or if suppose smoke is being detected. So first, initially smoke is going to be detected, and then fire is going to be detected. So in here, it is going to compute this information. It has detected that fire has occurred. It is going to open the water sensors. That is, based upon the fire alarm, the water sensors are going to be activated. And in here, as fire is being detected, this fire alarm system has got a mechanism where you can send message to the owner of the house that fire was started within the specific area of your home. So that information is transferred through a network switch or a telecommunication device. You might get now this network switch, you can get information that fire is there in your house at a specific location. And then here, by making use of a telecommunication device, it can also send a message to the fire department to send a fire brigade to put out the fire. So this is how the hardware is going to work. The next is people. People are users and operators of hardware and software. The people that are going to work upon this hardware and software, those are called as your people. The next is database. Now, what is a database? A database is a large organized collection of information that is accessed via a software. Now, whenever you're designing a particular software, now if as we have taken the example for the fire alarm system, within this fire alarm system also you need to feed in the fire department number, and you need to feed in your own contact number where you're going to get this information. So this is stored within the database. All of your information, the fire department number or your contact information, it is stored within the database. From within your database, that this messages are going to be sent. So in here, database is a organized collection of information that is accessed via a software. The next is documentation. Documentation is descriptive information. Now, what is descriptive information? It can be, it is a hard copy, it can be a manual or a report. So these are descriptive information that portrays the use and operations of the system. Now, whenever you buy this fire alarm system, you're going to get a manual along with it. Now, this manual is going to describe in detail what are the functions that this fire alarm system is going to provide. What are the different settings? What are the different settings within this fire alarm system? That everything is going to be documented. Now, each and every software that you purchase, you're going to get a manual along with it. That is the documentation. The next is the procedures. Now, procedure is the steps that define the specific use of each system. That is, what are the steps that you're following so that a specific task can be achieved. Use of, or the procedural context in which the system resides. It is going to have the description of all of these elements. Now, these different elements, they combine in a variety of ways to transform information. These elements combine in a variety of ways to transform information. All the elements, that is the software, the hardware, the database, people, procedures, and documentation. I'll take an example for this. Suppose you've got a robot. Now, this robot is going to transform every command file that contains, now the command consists of certain instruction. Now, this robot is going to transform each and every command that has instructions into a set of control signals. Now, these control signals, this cause some physical action. Now, this physical action can be the robot moving forward, the walking, or carrying something. So these are the different tasks. How like this is an example of how instructions are transformed to complete a physical action. Now, coming on to the example. Now, within this, if we take an example of a factory automation system, that is wherever multiple products or software are designed in a bulk. That is a factory automation system. Now this factory automation system, it is going to have different levels of hierarchy. Now different levels of hierarchy means the different controls that are assigned. Now within this, you're going to have different levels of control. And here, at the lowest level of hierarchy, at the lowest levels, the different things that you're going to have are control machines, you can have the robots or any data entry devices. That is at the lowest level. At the lowest level of the hierarchy, you're going to have different control machines, robots are going to be assigned, and different data entry devices are kept, so that whatever in what is so that you can keep a track of whatever work is being done in here. And each of this control machine, these robots, these data entry devices, each of them is a component based system, because it is going to take input and give a specific output. These are the component based systems. Now if we come on to the control machines, now within this control machines, you're going to have different electromechanical hardware or electronic stuff is going to be there. So if we go for hardware, within the hardware, we're taking the examples of control machines in here, the first one. Within the control machines, the hardware can be the processor, it can be the memory, or it can be the different sensors. Whereas coming on to software, now by making use of the software, you're going to perform communication or given different machine controls, what the machine needs to do, the specific task, or interpolation, that is entering some specific values, that is giving input to the software. Then the next one is the database. Now the database is going to be the program that is used for the production of the software, or that is installed in every component based system, that is the control machines, the robots, or the data entry devices. Then next is the documentation. Now what is going to be within the documentation? You're going to have different manuals or reports. Whereas within the procedures, you're going to have the actions that you're performing to complete a specific task. So this is the lowest level of hierarchy, the different component based systems, and within the component based systems, what are the different components that are used within the what are the different components within the control machines that is identified in here. Now at the next level of hierarchy, you can have the manufacturing cell. Now within this manufacturing cell is also going to have different computer based system. You're going to have different computer based systems, and these computer based systems are going to have different elements of their own. Now what are the examples for these elements? That is the different computers or the different mechanical fixers. That is, suppose there is any fault within the system, how you're going to fix those faults and how you're going to integrate the different elements within the software, or everything is given within the manufacturing cell also. The manufacturing cell also has a component based system of its own. The next is the system engineering hierarchy. Now within the system engineering hierarchy, the system engineering encompasses of a collection of top down and bottom up methods to navigate the hierarchy. Now within this, the system engineer hierarchy, you're going to have top down and bottom up approaches. That is, you're going to start from the top to the end or from the end to the top, so that you're going to navigate the hierarchy. Now let's move to the next slide. Now this is the system engineering hierarchy. Now the system engineering hierarchy, it starts with the worldview. The first view is called as your worldview. Now within the worldview, if you even see the globe from the top view, you're going to have a just brief description, or you can say you're going to have a broader view towards everything. So the worldview also captures the broad view of a particular system. The entire business or the product domain, that is the entire business or the product domain is going to be examined, so that you ensure that the particular, it ensures that you can have a proper business and you have the proper technology, so that you can complete a particular task. The business and product domain is examined, so that you can ensure the proper business or the different technology context is established. That is, you're going to have a broad view on two things, that is whether you can perform business and the different technologies that are going to be used within this system engineering hierarchy. Now, as from the top view, from the world view, you're going to start from the broader view. Whereas when you go down to the later levels of the hierarchy, like from the, when you're following the top down approach, you're going to have more simplified, or you're going to have more detailed representation. As you go down, you're going to have a detailed view of each and everything. Now within this process, whenever you're examining the business, product or domain, you're going to identify the domain of interest. Now what are the domain of interest? It means the different areas of interest. Now within the, whenever you're designing a particular software, the different domains of interest can be the manufacturing field. Manufacturing is one domain, engineering is another, marketing and finance. These are the different domains. Whenever you're examining a business or a product domain, you get to know the different domains of interest. This is again a more broader view. Now when you are going to move from the domain view to the element view, what is going to happen? Each and every domain is going to make use of different elements, so that a particular task can be completed. What are the technical activities that you're using? The different technical activities or the different hardware and software that you're going to use, each is going to be defined. That will be your different elements in here. The hardware, the software, the different technologies or the different techniques that you're going to use, that is going to be your element view. Now this element view is used within the domain view. That is one part, each and every part, this one part, this is called as your system element. This is another system element. This is another system element. Whereas when you go on simplifying each and every software and hardware, you're going to have more detailed view of the implementation. That is what needs to be done. Now within this detailed view, you're going to go for the construction part. You're going to go for the designing and construction part. Design and construction of the target system. That will be your detailed view. Well, you're starting from a broader view, and you're going to identify the different areas of interest and the different techniques and tools that are going to help the domain to complete the task, and then more detailed representation of the analysis, design, construction, integration of each and every element within the software. Now, the worldview in here is defined as WV. Worldview is composed of a set of domains, as we have seen within the previous diagram. Different domains are there. Now in here, which can each be a system or a system of system. That is, in here, each and every domain, it can be one specific problem or it can be a sub problem that will be identified on its own right. So in here, the worldview is defined as the different domains. Domain 1, domain 2, domain 3 goes on to the n number of domains that you have. Then as we have seen within the previous diagram, each and every domain has got an element. Now within this, you have seen the worldview. Worldview contains of different domains. D1, D2 goes on till Dn. Now this domain is also going to consider of different elements. Now these elements are, each domain is composed of specific elements that are represented by E of j, each of which serves some role in accomplishing the objectives and goals of the domain or the component. So in here, we have seen the different element view. That is, what are the different hardware that can be used, or the different software engineering practices that are used, or the software that you are going to use. These are the different elements. So in here, within the domain, you're going to use different elements. This is going to go on from EI to EN. That is the different set of elements that you're using. Then finally, each element is implemented by specifying technical component C of K that achieves the necessary function for an element. That is, each and every component, each and every element is going to make use of a technical component to complete the task. That is, E of j is going to consist of different technical components. Now in here, the different technical components can be a computer program that you're using, it can be a reusable program, it can be a module, a class or object, or even the programming language statement. These all are your components. These are the examples for components. The example for elements, it can be the different hardware, software you're using, or the different technical tools that you're using. Then the domains are your areas of interest. So this worldview portrays a clear definition of the overall functionalities that will enable the engineer to understand the domain and ultimately the system or product within the proper context. So this is what the worldview is going to give you. Then the next topic within this is system modeling. Now modeling the software means you're going to create a model. As we know from the previous unit, modeling is you're going to create different models. Now these models are created so that you identify the different requirements that are required within the development of a particular system. Now system engineering, it is a modeling process. That is, whenever you're designing the software, this is called as your modeling process. Now within the modeling process, you're going to focus upon the worldview. As you have seen within the previous slide, the worldview gives you a detailed description of all the functionalities of the system. Worldview gives you all functionalities within the system, or the detailed view within the detailed views within the lower levels of hierarchy. You're going to have detailed description. The engineer is going to create models that is going to define the process. That is, what are the actions that are going to be used within the development of software. You're going to define all the actions that serve the need of you under consideration. That is, the ones that are important. You're going to define each of the action. Then you're going to represent the behavior of the process and the assumption. Now behavior means what are the external factors that can affect the development of the software that is going to be identified. Or behavior of the system means how the system is interacting. That can also be identified. Now when you know how the system is going to interact, it becomes easy for you to create a model. The next is explicitly define exogenous and endogenous input. Now in here, exogenous means external. Endogenous means internal. What are the different types of input? That is, whether the input is going to be collected internally, that is from one component, the one task is being completed by one component, so this one is going to give output to the second component, whereas this output of one is input for the second one. So you get to know what are the different external and internal inputs the system is going to get. Now internal inputs is going to be what are going to be given by the specific components, whereas external inputs is what the user is going to give the input externally. Then the last point is represent all linkages including output that will enable the engineer to better understand the view. That is, in here you're going to identify all the interfaces within the software. Now interfaces means how the external and internal interfaces are going to be identified, that internally how they are going to be connected, externally how they are going to be connected. Each of these interfaces are going to be identified. So this is system modeling is going to focus on these four aspects. To construct a system model, the engineer should consider a number of restraining factors. Now the first one is assumptions. Now what is an assumption? Assumption that reduces the number of possible permutations that enable a model to reflect the problem in a reasonable manner. That is, in here you're going to identify and you're going to focus on all the different things that you're going to assume certain scenarios, how the system is going to behave. All of the things are going to be identified so that you can reduce the number of permutations or the number of variations for the particular software, so that you can define each and every step in a reasonable way. That can be identified. Now if we take an example for assumptions, now within an example for assumptions, if suppose a company is designing a 3D human form. Now whether this 3D human form means you're designing a particular robot. Now whenever you're designing a robot, you're going to design focusing on a specific human. That is, what are the differences between a human and a robot. You're going to specify what are going to be the leg movements. Now within the leg movements, you're going to make an assumption that the robot cannot wrap his legs, whereas if you go for arm movements, within the arm movements, a robot might not be able to fold his arms. So these are the different assumptions that are going to be made while you're designing a specific model. Now when you focus on these assumptions, now focusing on assumptions is going to help you design a model in a very reasonable way. That is, you get to identify what are the things that you can do and what are the things that can't be done. So this is the different assumptions. Whereas coming on to simplification, the simplification is going to enable the model to be created in a specific time. Now when you simplify the model, you're going to identify each and every action, you're going to simplify it. You're going to simplify it because if suppose you're designing a model that is very complex, it is going to take a lot of time. It is going to take loads of time. Whereas if you've got simple tasks to be performed, the simple tasks, if you have simple tasks to be performed, they can be created in a timely manner. That is, within sufficient time, it can be created. Coming on to limitations. Limitations are what is going to bound the system. That is, constraints. Limitations are basically constraints for a particular system. That is what can be done and what cannot be done. That needs to be identified. If we take here the example of you're designing an aircraft. Now an aircraft is going to have a limitation of two engines. That is, whenever a new aircraft is being designed, you're going to every aircraft is going to have a minimum of two engines, not more than that. So that is the limitation. You're not going to design the aircraft with one system or with one engine or three engines. You're going to have two engines within the aircraft. The next is constraints. Now, constraints are how a particular model is being created, or what are the different approaches that you're using to model the software that is going to be identified within the certain approaches. Now, within the approaches, you can identify the different programming language that you're using, the technology that you're using, or the processors that are supportable for the specific development of architecture. That are your constraints. The last one is preferences. Preferences indicates what is the preferred architecture. Now, preferred architecture means, now whenever you're designing a software, within the previous unit, we have identified that we identify what is the data that will be used, what are the different functions that are going to be used for developing the software, and the different technology. Now, which is the best, what is the preferred architecture, everything is being decided. Now, in here, all of this is decided to avoid any conflicts between the end users and the developers. At the end, customer satisfaction needs to be predicted, whatever approach you're following. So this is the system modeling. The next topic is system simulation. Many computer-based systems interact with the real world in a reactive fashion. Now, that is, the real world events are monitored by different set of hardwares. The real world events, they are monitored by set of hardware and software. Now, this hardware and software, they combine and they form a computer based system. Now, as you've taken the example for the fire alarm system, so based upon this, based upon the event that is detected by this reactive system, it is going to take a specific action. These type of systems are called as your reactive systems. Real-time and embedded systems often fall into the category of real-time systems. That are your fire alarms, it can be the sensors, all types of sensors. It can be your fire sensors, the movement sensors, different types of sensors, door sensors. These are all your embedded system application. That is your reactive systems. All of this embedded systems and real-time application, these are called as your reactive systems. Now, these reactive systems, they are designed in such a way that allows multiple applications are blend together as one single unit, and this one single unit, it reacts to the environment. Like the example of sensors. Now, it is going to react to this environment, and it is also going to be aware of the different sensors that are present within the house. Many systems in the reactive category and control machine, that is, what are reactive category and control machines? Now, within this reactive category and control machines, you can have the example of commercial aircraft or petroleum refineries. So, this is also an example for reactive systems. or processors that might operate with an extremely high degree of reliability. Now, in here, whenever you're dealing with a commercial aircraft, or whether you're operating with a petroleum refinery, you need to be very vigilant of what is being designed. You need to design the software so that it has got no fault within the system, because any fault within an aircraft or a petroleum refinery, it is going to lead to loss of human life. So if the system fails, significant economic and human loss could occur. That is why any type of software that are designed, they are going to be focusing on no faults for developing the software. Software tools for system modeling and simulation are being used to help eliminate surprises. That is, you're going to make use of specific tools whenever you're modeling the system, so that you can make assumptions what is going to happen, or you can predict the faults, and you can fix any type of errors, or you can have a backup that can be used in a type of situation. These are used to eliminate surprises, so that this type of situation does not arrive when the aircraft is full of passengers. So whenever you're designing, you're going to make of specific tools so that you can make different assumptions, predictions, and you can be planned for any type of you can be prepared for any type of situation. Now, modeling and simulation tools, they enable the system engineer to test drive a specification of the system. That is, in here, these software tools and systems, these are used so that you can test drive. That is, if suppose if so and so scenario has occurred, how the system is going to behave, how the system will behave, that is going to be identified. If the system is not behaving well, you're going to make changes within the software. You can refactor the code, you can fix the issues, and the software will be ready. So within today's class, we have studied the topics. First, the computer-based system. Now within the computer-based systems, now these computer-based systems take input and they process output. Now based upon this computer-based system, these computer-based systems make use of certain elements to complete the task. Now within this, you've got the software, you've got hardware, you've got people, you've got the database, documentations, and procedures. Within the computer-based system, we have studied this. We've also taken the example for a factory. Within the factory, the different elements that are used are the control systems, robots. Each of the things are control-based system. This control system, robots, or any machinery, these all are examples for computer-based systems. Now, when you focus on this control-based system is also going to make use of all this 6 elements are going to be used within each control system. We have taken examples of different hardwares, softwares, people. Within the software, the program that is being used within the system, the hardware. Within the hardware, you identified the different processors that are used. Within people, the users that are using the software, the database where you're storing the information, documentation and procedure are documentation is going to have the full description of all the software, hardware, people, and databases, and procedures is going to consider of different actions that are used within the software. So within the first part, we have studied the computer-based system. Within the second part, we have studied the system engineering hierarchy. Now within the system engineer hierarchy, we have studied the worldview, the domain view, element view, and component view. The worldview is going to have different domains. Domains are your area of interest. Examples of area of interest were finance, it can be finance, it can be marketing, it can be manufacturing. Then within this domain view that is represented by DI is going to make use of different elements. E1, E2 goes on till EM. Now these elements are used so that you can achieve a specific goal or objective. And each element that is defined by EJ, each element is going to make use of technical components that goes on till CI to CK. Whereas this components, it can be a program, it can be a component or module. Now in here we have studied that within the worldview you're going to have a broad view of what is being used within the software. Whereas when you go on to the component view, you're going to have a detailed view of the software. That is, you're going to have detailed description of each and every component elements and how you're going to implement the software. Details of construction, design, and integration. Then within system modeling, we've studied about the assumptions. We're taking the example for development of a 3D model. Then simplifications so that you can deliver the software in a specific time. Then the limitations, the constraints. Limitations are what is going to bound your system. What are the restrictions? Constraints are going to be what is the type of processor that you're using. Then you go for preferences. Preferences is the type of data, the different components that you're using. You're going to have a architecture, and this the preferred architecture. Within this, that you're going to have data, you're going to have the functions, and above all this, we are going to focus on customer satisfaction. This is the overview for the syllabus that we have studied today. In the next class, we'll be studying the business process engineering. Thank you.